In this poster, I am showing my work on how we can determine and compare the electronic conductance of DNA and RNA using extensive simulations, and then how we can predict these results using ML methods. So first we use a multi-scale methodology where we perform all atomistic MD simulations to get the dynamics of DNA RNA sequences, then perform DFT to get the electronic structure, and then kinetic Monte Carlo simulations to get the charge dynamics using Marcus-Hersh formalism. Using this, we find that the DNA conducts better than RNA, and the reason is that RNA sequence is more disordered than DNA. Now, to predict these results and more, we use a deep neural network where the base pairs are represented by Coulomb matrices and used as input features. And then we predict the using this neural network, we predict the electronic coupling between any two base pairs. Using this model, we get the same trends for DNA RNA conductance, and we get the same result in fraction of seconds what would have taken 97 days using DFT. We also use this ML method to detect the presence of single mutation using electrical conductance. In conclusion, we find that DNA conducts better than RNA and devise an ML model to predict the conductance of any DNA RNA sequence. Thank you.
Quantum coherent dynamics model using non-metallic endohedral fullerenes.
Thanks for visiting our poster, and I'll be talking about some work that we've been doing on the computational screening of small molecule organic semiconductors. So we developed this whole procedure. It starts with an input of smiles and smart strings, which defines our search space. We then run an evolutionary algorithm over that search space, optimizing for low reorganization energies and high electron affinities. So we'll get a list of molecules that the evolutionary algorithm has sampled, and we take the best molecules from that list and run a full crystal structure prediction with mobility evaluation for each crystal structure within an energy window from its global minimum. From this, we can get some idea of which molecules is most likely to form a high-performance organic semiconductor based on their certain properties such as their electron affinity and their landscape average mobility. So we hope we can use this to run a search and propose the best molecules for experimentalists or other computational groups.
Hello everyone, I am Jyotirmoy Dev, working as a Senior Research Fellow in the Department of Physics, Assam University, Silchar, India. Here I am going to present a newly proposed carbon electrode, namely pentagraphene, and confirm its stability based on the state-of-the-art theoretical calculations such as energetic stability, dynamic stability, mechanical stability, and thermodynamic stability. Our results reveals that this material is a wide bandgap semiconductor having superior optical property along with ultra-high carrier mobility. Based on these properties, we may conclude that this material is a potential candidate for future nanoscale electronic devices, optoelectronic devices, and photovoltaic applications. If you are interested to know more about my poster, then please visit my poster having poster number 04.
Hi, I'm going to be talking about the mechanoelectric response of single crystal rubrene, which we studied using ab initio molecular dynamics as well as transient localization theory. The reason for using such a high-level method here is because of several contradictory experimental and theoretical reports in the literature. So here we go beyond the harmonic approximation for lattice dynamics and the linear approximation for electron-phonon coupling, and ultimately we find that compression causes an increase in mobility, and that the increase in mobility is larger when compression is applied along the direction perpendicular to the high mobility axis. So this is a consequence of a significantly greater suppression of electronic coupling fluctuations when strain is applied along this direction, highlighting the importance of considering off-diagonal electron-phonon coupling in these problems. I look forward to talking to you during the poster session.
Hi, my name is Daniele Fazzi from the University of Cologne, and here I report our recent investigation about modeling of polarons in ladder-type conjugated polymers. We focus on BBL, which is a high conductive ladder polymer showing insulator to conductor transitions upon doping. Experiments suggest that multiple polarons should form. However, it is unclear the correlation between the high conductive states and the charge states of the polymer. We calculate multi-redox states, meaning different electron per repeat unit. They show multi-configurational character and high spin and energy degeneracy. Finally, we correlate them with the observed conductive and insulating states. Let's discuss the details in the virtual room. Looking forward to meeting you there. Bye!
Hello everyone, I'm Soria from my side from Al Faisal University. This work is about experimental and theoretical investigation of direct growth of nanoparticle based on nickel, cobalt, and sulfur in order to make DSSC and replace the platinum electrodes. We use also theoretical model in order to validate the IV characteristic and the calculations for the parameters of the cell. So technically we use nickel nitride, cobalt nitride, sulfur and mucosal detergent. We also characterized our materials using STM and XRD diffraction. Also, we studied the chemical state over the surface analysis with X-ray photoelectron spectroscopy, and also we recorded the IV characteristics. As it's shown, there is a good fit between the experimental and theoretical work, and this work was published in SolMed this year. Thank you so much.
This work is a computational study of the photophysics developed in pure carbazole crystals after electronic excitation. Carbazole and its derivatives are probably the most used systems for optoelectronics. However, the photophysics and photochemistry pathways of electronically excited carbazole in the solid phase have not been addressed before. In this work, we studied the de-excitation mechanisms of carbazole by computing experimentally measurable magnitudes as emissive and electron transfer rate coefficients through the different channels in the crystal. We studied the aggregation effects and also what happens when a carbazole isomer is acting as an impurity of the crystal. These results are important because very recently it has been proposed that the ultralong organic phosphorescence commonly observed at room temperature in carbazole-based systems is not a property of the molecule itself, but it is provoked by an impurity of a carbazole isomer generating molecular heterojunctions that could pave the way to new application in optoelectronics.
Unraveling the mechanisms and timescales of free charge generation at organic bilayers is rather challenging because the electronic couplings, static disorder, and electron-phonon interaction are all comparable to one another, which invalidates the use of simple theories of exciton and charge dynamics. In this contribution, we employ the modified Redfield theory, which interpolates between the standard Redfield and Förster theories and thus enables us to capture the interplay between the localization, disorder, and polaronic effects during charge separation. We find that charges are separated via the cold pathway irrespective of the excess energy of the photogenerated donor exciton. We observe that charge separation is prolonged for stronger disorder, which hampers charge transport toward contacts. We also find that the separation yield relatively weakly depends on the electron-phonon interaction strength. In case you are interested, please come to poster number 9.
Electron transfer is the key step in many biological and chemical processes and has important applications in electronic devices. However, electron transfer rates are difficult to obtain using Marcus theory, as many parameters are unknown. We present a binless version of the dynamic weighted histogram analysis method to determine free energy profiles of reactions based on biased molecular dynamics simulations. The method is then demonstrated on the aqueous ferrospheric electron transfer reaction. Classical MD simulations are performed on intermediate partial charges of the iron cations between +2 and +3 to sample the reaction coordinates sufficiently. Then the free energy of the adiabatic ground state is determined by introducing electronic coupling between diabatic states and unbiasing simulations with binless DHAM. Key feature of our method is that it yields electron transfer rates directly. We compare these rates with those from the I-ring equation and show that with appropriate choice of the electronic coupling value, the results can match the experimental electron transfer rates.
Dear colleagues, good afternoon. My name is Dimitrios Kokinos. I'm a physics PhD student with Bath and Chester University, and I'm here to present you my work in charge transport on polymer organic semiconductor materials, and especially in the case of PFO with particular interest in the effect of torsional dynamic disorder in our system. Our work is trying to establish an upper limit of intrachain mobility, and by adding degrees of freedom or kinds of disorder to match the experimental data. The classical part of our model Hamiltonian enables the interaction of the dynamic disorder with the wave function delocalization process. A crucial point in our approach is the introduction of transfer integral as a function of the hydral angle rather than a fixed value. We observe a good agreement of our mobility values with experimental data in respect with the level of the theory applied.
Hello everybody, this is a short introduction to my work presented at the Congress called the ligand's effect on the photoinduced charge transfer in chromophore-labeled gold nanoclusters. So within the real-time time-dependent density functional binding method, we perform non-adiabatic molecular dynamics within the Ehrenfest approach in order to study the optical properties and the charge transfer processes in an exit-protected gold sulfur cluster labeled with a pyrene fluorophore. We focus on the role of the ligand in the charge transfer processes, finding that when they are present, we can reach a stable steady state in the charge transfer processes, which is not the case when we don't have the ligands present. We also propose a three-step mechanism and shed light into the electron and nuclear movement coupling.
Hello, and welcome to my poster. My name is Giacomo Melani. I'm a postdoctoral fellow in the group of Marcella Iannuzzi at the University of Zurich. And this is a work done together with the group of Caterina Cocchi at the University of Oldenburg. Our work is based on a computational study to investigate the adsorption of few candidate molecules with acceptor-like, donor-like, or aromatic behavior onto a 2D hexagonal boron nitride surface. The aim of our study was to identify hybrid photoactive states between the molecule and the BN surface. And we did that thanks to DFT calculations highlighting density of states and orbital analysis. And if you want to know more, please come to my poster. Thank you.
6,13-pentasynquinone, an intermediate for the pentasyn, is synthesized by using mortar, pestle, and hydrothermal method without using any organic solvent. After synthesis, we have also synthesized pentasynquinone TiO2 composite and coupled system. Structural characterization is performed by using XRD and NMR. Morphological characterization is performed by using SEM and TEM microscopy. Now, after complete characterization, we have explored all these systems for organic degradation as well as for hydrogen generation from H2S gas. PQ can be useful for multifunctional applications like H2S splitting, water splitting, formation of pentasyn, gas sensing, solar cell.
Hello everyone, I'm Pavel Rukin from CNR Nano S3 Modena. At my poster you will find the study of internal conversion between B and Q bands in a functionalized porphyrin. The study is based on displaced multi-mode harmonic oscillator approximation. This model helps to understand vibronic structure of the system states. In this model, the displacements of the normal modes are represented in Huang-Gris factors, which gives the main contribution to the internal conversion rate through Frank-Condon factors. The Huang-Gris analysis provides us the selection of the active modes. Using them, we can respectively well reproduce the rate constant and the time of internal conversion between B and Q bands. But the main advantage of detecting the active modes is that we can take a look inside of the electronic structure along them and extract useful information. Everyone who is interested which one is welcome to take a look at my poster.
Hello, this is Mihir Ranjan Sahu from Harishchandra Research Institute, India. My topic is magnetic state transitions of manganese dimer on carbon dope HBN surface through external electric field. Using density functional theory, we first show that the interaction between two manganese atoms can be tuned from antiferromagnetic to ferromagnetic state by creating charge disproportion between the two atoms by customizing the ligands. The non-metallic planar heterostructures designed by doping carbon atoms in HBN sheet are considered as the substrates of manganese dimer to study the magnetic properties. This 2D platform is introduced to design a model analogous to the atomic cluster to manipulate the charge transfer from the manganese dimer to switch the magnetic states. External electric field is applied normal to the plane of substrate to control the charge transfer between manganese atoms and the surface. Depending upon the concentration of the carbon in a spin sheet and the strength and direction of applied electric field, magnetic states of the dimer can be switched from a antiferromagnetic to ferromagnetic and vice versa. Using these two magnetic states, ferromagnetic and antiferromagnetic, one can store one bit 0 or 1 information per chip. Thank you.
Hello, this is Dr. Keval Sonigra from Optoelectronic Technology Laboratory, Oxford Suzhou Center for Advanced Research, Overseas Research Center of University of Oxford in China. Here I have presented the phenothiazine benzimidazole architecture of an interfacial charge transport layer for perovskite light emitting diode. The two materials, BPS and BPS2, are studied in perovskite light emitting diodes in terms of mobility and its wettability compatibility towards the perovskite precursor solution. The BPS2 have a better wettability and gives the better EQE based perovskite LED device than BPS. Thank you.
Hi everyone, I'm Elif and I'm working on modeling charge transport in 2D COFs. COFs are crystalline porous materials which are potential candidates for the optoelectronic applications. Their physical properties can be feasibly tuned due to the structural diversities of the ligands. Millions of 2D COFs can be achieved by varying the cores and the linkers. Therefore, it is important to explore their properties systematically and to predict which material is promising. We are investigating transport mechanism via theoretical approaches, and our strategy is like this. For each structure in our database, we perform DFT-based calculations to obtain structural, electronic, and vibrational properties. Then we estimate the relaxation time by comparing different approaches such as deformation potential theory and electron-phonon coupling. Then, within the Boltzmann transport theory, we calculate the transport properties. These are the references. Thank you for your attention.
In this work, we study charge injection at metal-polymer interfaces for polymers such as polyethylene. Figure 2a is the periodic unit cell, and we will study the influences of 4 polar groups on charge injection. For each interface, we will study the structure at 0 temperature based on DFT, and then at 373 Kelvin by ab initio molecular dynamics simulations to obtain different interface snapshots. For each snapshot, we calculate the charge injection barriers using the method in Figure 3. In Figure 4, the results show that first, the average injection barriers can be tuned by up to 1.1 electron volts by different chemical groups. Second, different chemical groups can have different standard deviations of injection barriers. To understand this issue, we calculate the z-axis dipole of a chemical group shown in Figure 6, and we establish a general linear relationship between z-axis dipole moment and electron injection barrier among all groups in Figure 5.
Hello, I'm Feder Gaumans with Software for Chemistry and Materials. If you want to optimize a new OLED material, you need to optimize the properties of each of the individual materials. So for instance, luminescence properties, charge transport properties, as well as how the entire stack of materials comes together in the OLED device. And this is exactly what we want to do in a single platform where we combine our atomistic methods in the Amsterdam Modeling Suite with the kinetic Monte Carlo methods in Symbion's Bumblebee Suite. So you can optimize simultaneously the properties of each of the individual materials at the molecular level or atomistic level by, for instance, calculating phosphorescent rates, charge transfer rates, exciton transport rates, and then putting them together in the kinetic Monte Carlo code to optimize the materials and the entire stack simultaneously.
Hello everyone. Organic solar cells that made of organic donor acceptor bands have attracted remarkable attention, especially in recent years, since their efficiency exceeds 10%. However, the charge separation mechanisms in those materials are still elusive, with different research groups propose contradictory pathways even for the same material. In this study, we would like to extend our fragment orbital-based surface hopping method, which has been successfully applied to understand the charge transport mechanism in organic crystals, to include Frankel acetone states, so we can use the method to understand the organic donor acceptor bands systems. We first apply the newly developed method to a model system proposed by Irene Burkhardt group and compared to their NCTDH dynamics. We then discuss the charge separation pathways predicted by our method.
Multiscale simulations are the holy grail of molecular modeling. In my poster, I present a new coarse-grained model developed specifically for organic semiconductors. This force field is parameterized from the bottom up and is based on a robust partitioning of molecular energy, including electrostatics, short-range, and bonded interactions. Crucially, the model reproduces accurately the excluded volume of molecules, allowing the reverse mapping of atomic coordinates. The coarse-grained simulations yield exceptionally good properties, both static and dynamic. This model requires fewer computational resources and does not compromise on the quality, allowing the study of mesoscale samples, as shown in this example. My name is Otello, and my poster is number 22. See you there!
Organic fluorophores with enhanced emission in aggregate phases with respect to the vacuum solution, also known as aggregation-induced emission, have a great potential for the design of optoelectronic devices. One of the important classes of molecular crystals which exhibits aggregation-induced emission are propeller-shaped systems. In this study, we examined the excited states relaxation mechanisms of three propeller-shaped systems. The first, which is based on cyclopentadiene and shows a strong aggregation-induced emission. The second system is based on the thiophene molecule and shows a weak aggregation-induced emission. And the third system is based on furan and doesn't show aggregation-induced emission. It is characterized by aggregation cost quenching. We apply static and dynamics quantum chemical approaches to study in detail the mechanisms of inter- and intramolecular non-radiative decays and fluorescence in order to explain the differences in their emissive properties.